This video is about radical expressions and functions. We'll begin with a definition which states this. If b squared equals a, then b equals the square root of a. And of course, the symbol for square root is kind of like this jagged, roof that goes over some kind of number or variable. Okay, secondly, if b cubed, b to the third power equals a, then b equals the cube root of a. So it's the same little symbol for the root, except now you have a little number kind of tucked in the corner of the symbol, and that number is known as the index. Okay, and so if you don't see a number written there, like in the first case with the square root, there was no number written there, you assume that it's a square root, and therefore you could imagine a number 2 written there as the index of 2 for square root. But otherwise, if it's not square, you have to see the number written in that little place as the index indicating which kind of root it is. Now let's explore, just to understand how these definitions work. We're going to make a little input-output machine here, and in the first case of what we're exploring, I'm going to put the number 3 buried inside this little machine. Now, what is this machine? Well, this machine is something that will do two things. It will square that input number, and then it will take the square root of that input number. So if we follow those operations one little step at a time, then after squaring that input number of 3, we would get 9. That's the first operation. But then we would take the square root of that 9 and end up with 3. So you can see that the output number ended up, in this case, also being 3. We went from 3 as the input, we got 3 as the output. Okay, notice in the second case of this, we're going to use this time -3 as the input number, but we're going to put it in the exact same machine. That is, we're going to square it first, and then we're going to take the square root. So when you square first, using order of operations, you get a +9 because you're squaring -3 in parentheses there. When we take the square root of 9, using the definition listed above, we end up with +3. So notice what's happening here. We are in a scenario where we're trying this input-output machine, but we've put in these two first cases a +3 and a -3 as the inputs, but in both cases we got a +3 as the output. So this is interesting. When you put a positive or negative number into something and you get the positive version only output, that's the same as an absolute value, as you may recall. In general, from these two cases, we could say, and you could demonstrate this with other example inputs as well, but in general, we could say that if you have the square root of x squared, which by the way is what the left sides of our little experiments were, it equals the positive version only, as we saw. That's known as the absolute value of that number. And so we can say in general the square root of x squared is equal to the absolute value of x, simply by matching up those definitions with this little experiment here. Okay, well let's go ahead and try another variation of this experiment. This time we'll do something similar, except we'll start with a cube root. So we're going to now use an input value. We'll even pick the same value. We're going to put +3 as the input, but this time we're going to cube it and then take the cube root of it. Well, when you cube 3, you get 27, and then when you take the cube root of 27, you get 3. So we're following a very similar path through this little experimentation math machine here, except we're using now a cube root. And notice when you put a 3 as the input, a +3, you get a +3 as the output. Okay, this time let's use that same cube root machine, but this time put a -3 as the input. Well, when you cube -3, that's really -3 times -3 times -3, then you get -27. But when you cube root -27, you get a -3. So it turns out this time we're not getting the same kind of result. We're getting something quite opposite. In fact, or not opposite, but just different. So when you have a positive or negative input, those signs stay with the outputs. One other way to say it is that odd roots respect negatives. If it started positive, it stayed positive. If it started negative, it stayed negative. Now, we have to be very careful with these differences. We're going to add in some notes about the notation here next. It turns out that the square root of 36 equals 6 because 6 squared equals 36. That follows exactly with the definition we started with way above. Okay, but isn't it also true that negative 6 squared is positive 36? So what does that tell us about how we can represent that kind of notation? Because you can see what we've seen here is a couple examples where we're putting a positive 6 squared is 36. That's why the square root of 36 is 6. That follows the definition above. But hold on, negative 6 squared is also 36. So is it the case, as we may suspect, putting these definitions together, that the square root of 36 is also negative 6, right? That's the kind of the question we're talking about here, because that would fit the definition with this little example. Well, it turns out that the positive root, so in this case the positive 6, is called the principal root, and that's why we would say, 6 squared, positive 6 squared is 36. So that positive value, known as the principal root, that's what we use for this square root symbol. In fact, the square root of 36 is not equal to negative 6 to answer our question that we posed directly above. So this is a often overlooked or misunderstood part of this notation. When we say square root of 36, it is not negative 6. It's only the positive or principal root. So this symbol, square root, only refers to the principal root. We will never see a square root symbol of something equal to a negative value. All right, so that's a big deal, really just dealing with the notation, but it's truthfully the cause of many confusing results, and so we'll see it hopefully played out as we continue through these examples. Now let's actually try some more examples that use this notation. The first of which is negative and then a square root of 16. So the negative sign is outside in front of the square root symbol, and then underneath that square root symbol we have the number 16. Well, we can evaluate that with no problem. We're just going to leave the negative sign out front and then handle the square root of 16 as we see it with the definition way above, which would be simply 4. So negative 4 is the result of this expression. Now, contrast that with the second example, which begins as the square root of negative 16. So this time, the negative sign is inside the square root in front of the 16. Well, in this case, we actually end up with a problem because what number squared would give you negative 16? Right, that would be the way to kind of write the square root using the definition above. So what number squared is negative 16? Well, no number squared is negative 16, because when you square a number, whether it's positive or negative, the result will always be positive. So you'll never get a negative value when squaring something, which means our official answer for this, as of yet, this will eventually change, but our official answer for right now is not a real number. That almost seems like a answer begging for more information, and it is. And perhaps at this phase, you've already seen some other ways to get around that and explain it. We'll eventually get there, but we're not there yet. All we're saying right now is not a real number. In other words, we can't take the square root of a negative value. Moving on to our third example, we have here negative and then square root of a fraction, which is 4 over 25. Well, it turns out that, first of all, the negative is out in front, so that's no problem with the negative there. The negative is only a problem when it's underneath the square root, as we saw in the previous example. Secondly, when you have a square root of a fraction, you can turn it into the square root of each part of that fraction, written one above the other. So the square root of 4/25 is the square root of 4 over the square root of 25. Of course, those are each roots that we can handle individually, so we're going to keep the negative sign out in front. The square root of 4 is 2, and the square root of 25 is 5, and so negative 2/5 would be our simplified result for that example. Now, we do have to be a little careful with something before we try our next example, and that is when you have the square root of a plus b, or the square root of a minus b, it turns out those results are not the same as, so be careful with this, it's not the same as square root of a plus square root of b or square root of a minus square root of b. In other words, you can't, if you have multiple terms underneath a root, as these two little examples begin here, you can't split the root up and take the root of each number individually, as would be shown on the right side here. This is not okay. So when you see something like, as our next example states, the square root of 25 minus 144, and that's all underneath the square root, it's tempting to say, oh, hey, those are nice square numbers. The square root of 25 is 5, the square root of 144 is 12. So isn't this just 5 minus 12? No, that would not work given this warning we have written here directly above. Rather, the only way to handle this is to simplify what's underneath the root first. We have to combine those two like term numbers. 25 minus 144 would be a negative 119, which leaves us with the square root of negative 19. But as we saw above, you cannot take the square root of a negative number, so we'll simply say not real or not a real number. Now, speaking of roots, let's move into a slightly different categorization of the same topic and talk about the domain of a radical function. We've already talked about domains previously in rational functions. You may recall in domain previously we cannot divide by 0. Well, now, given what we just saw above, we have a new consideration for domains. When you have a radical function, turns out we cannot take an even root of a negative number. Now you may say, wait a minute, that seems a little bit more general than we were just talking. We only did square root. Why are you talking about even root now? Well, it's because it actually is more generally true, though we only saw it so far in the case of a square root. For example, we saw that the square root of negative 4 is not a real number. Now, when you see an example that asks you to find the domain, which we'll look at next, we have to just do this one consideration. So our first function here to consider is f of x equals, and then we have square root of x plus 2, where the x plus 2 is all tucked underneath this square root for this function. Well, if what we just said above is true, then we can only take the even root of something positive, not negative, positive or 0, that is. Okay, so what that means for this function is that what's underneath this root symbol, so in this case the x plus 2, that expression has to be non-negative. So let me say it this way. If we take x plus 2, we could write that out as x plus 2 and say that it has to be greater than or equal to 0. So it could be 0, that's not negative. The point is it cannot be negative, so it could be 0 or positive, which is what the greater than or equal symbol means. So x plus 2 is greater than or equal to 0. Now we solve this using the inequality stuff we already know. Of course, subtract 2 from both sides, and you'd end up with x is greater than or equal to negative 2. So that's the final result. This is what we must have because x cannot be anything but 0 or higher in order to be underneath a square root. That's what we just discussed. So the general summary of this using interval notation is that we could say our domain is, using interval notation, we'll put a bracket on -2, comma, infinity. That would mean -2 or higher. And that's exactly what this statement indicates that we just solved in our previous step. So our domain in interval notation is a bracket with -2, comma, infinity. Okay, let's try the same kind of thing with another example. If you want to pause the video and try this one real quick on your own, that's a good way to practice this. But go ahead and think through it. This function is given as f of x equals 3 times and then a square root containing 8 minus 2x. So the 8 minus 2x is all underneath the square root. Now the initial setup on this one is the trickiest part. So if you've already paused the video to try it, let's see how this went for you. As we saw previously, we know that we cannot let what's underneath a square root be negative. Well, in this case, that's the 8 minus 2x. Notice there's this 3 out in front. That has nothing to do with what's underneath the root, so we actually don't even consider it or care about it for the domain. We're simply looking at what's underneath the root, in this case 8 minus 2x. We know that what's underneath the root cannot be negative. That's another way to say it has to be greater than or equal to 0. And so we'll solve this inequality just like we were solving it before. This will give us a -2x is greater than or equal to a -8 if I subtract 8 from both sides. Of course, to get x alone, I'll have to divide by -2. That means I have x, but if I'm dividing by a negative, remember we have to flip the inequality symbol. So that would mean x is less than or equal to a +4. Okay, so if I back that up, maybe I should show those steps here real quick. I'm just dividing by -2 on both sides of this inequality, but when you divide by a negative, that's when you have to flip the inequality symbol. And so now I have it facing the opposite direction, which means now we have x is less than or equal to. On the right side, we have -8 over -2. That's just a +4. So if x is less than or equal to 4, in interval notation, that would be a -infinity as the left boundary, so with a parenthesis surrounding it, comma, a 4, but an inclusive boundary with a bracket because it's less than or equal to, and that would be the domain for this function. Let's try yet another example. This third function reads as follows. F of x equals, and then we have a fraction, a large fraction, where the numerator is the cube root of x, and the denominator is the square root of 80 minus 5x. So that's all underneath that root there, 80 minus 5x. So let's recall for domain what we already know. We discussed way back in rational function land that we cannot divide by 0. We've seen that a lot by now. That remains true. Okay, that's always going to be true now. But secondly, what we've just added is that we cannot take an even root of a negative. Now, the only even roots we've been seeing so far have been square roots, but it's true even if we had a fourth root or something even higher than that. And of course, that would refer to the index number shown in a root. Okay, so we can't, or to consider domain so far, we have to consider these two keys or these two definitions and avoid them or look out for them when defining domain. In this function, let's consider whether we're going to hit either one of them, potentially. Notice that this function has a fraction involved. It's a large fraction with a variable in the numerator and the denominator, which means it's possible, perhaps, that I might divide by 0. Because with a variable in the denominator, maybe there's something I could plug into that variable that might cause it to be 0, and I can't divide by 0, so I have to make sure I avoid that. But then secondly, I also am not allowed to take the even root of something negative. So I'm actually going to combine both of those considerations in this problem. So in fact, we'll do this maybe with a couple different colors to help color code this. We'll make the first consideration that we cannot divide by 0. I'll do that one in blue. And the second consideration that, of course, we can't take the even root of a negative, we'll do that one in green. Now, let's do these one at a time. The fact that I cannot divide by 0 means that my denominator expression, which is the square root of 80 minus 5x, I can't let that be 0. But I really then would like to know, when does that equal 0? Because that would tell me what I have to avoid. So I actually set it equal to 0, and then solve to find out when that would happen so I know what to exclude. Well, to solve this, of course, if the square root of something is equal to something is equal to 0, then what's underneath that square root, in this case 80 minus 5x would be 0. Of course, if I then add 5x to both sides, I would have 80 equals 5x. If I divide by 5 on both sides, then I'd be left with, the 5's canceling, I'd have 16 equals x. Okay, so what's going on with that? Well, x equals 16 is actually a value we must exclude. Why do we have to exclude it? Because when x is 16, this expression of 80 minus 5x equals 0, but that expression happens to be our denominator, which we cannot let be 0. So we have to exclude 16. Okay, now that's only part of what we're considering. So let's kind of keep that aside and move on to our second consideration, which is that we cannot take an even root of a negative number. Well, we do have an even root, and that is in this denominator. So if I take what's inside that even root, which is 80 minus 5x, as we saw above when considering domain, that has to be greater than or equal to 0 in order to avoid what's underneath that root being negative. Okay, well, if I do the algebra to solve this, kind of like we just did with the previous inequality, we'd end up with an 80 on the left side. If I just add 5x to both sides, I'll have 80 is greater than or equal to 5x. Divide by 5 on both sides. Of course, I'm dividing by a positive 5, so I don't have to flip the inequality here. I would have 16 on the left side is greater than or equal to an x on the right side. So this is also what we must consider. But notice that we have to exclude 16 from the first case. Remember how we said we have to exclude 16 because we can't divide by 0? So how do we combine both of these statements in one summary statement? That's our question. How do I define a domain that represents everything being less than or equal to 16, but not including 16? If we put these both together. Well, if I simply take less than or equal to 16, that would mean I have the domain of negative infinity, comma 16 with a bracket around it for the less than or equal to. That's everything smaller than or equal to 16. That's actually what we have written for our second case consideration. But we said in the first case that we have to exclude 16, which means we're not allowed to use the boundary. So how do we fix it? Well, we simply go back and make it a curved parenthesis instead, because in interval notation, that means you're not actually using that number as part of the set. So our final domain of this one is parentheses containing negative infinity, comma 16. Okay, next, we're getting there. There's a lot in this topic, we're getting there. Next, we're going to graph with transformations, which will, of course, require us to recall the topic of transformations that we've done previously. And our first example to graph, and by the way, we're just sketching this, so we're not using a calculator even here. This would likely show up on a no calculator allowed kind of problem, perhaps. The first example here we're looking at is the function given as y equals, and then we have a square root symbol, and underneath that square root symbol we have negative x minus 40. Then after the square root symbol we have plus 30. Now again, we're going to recall what we already know about transformations, and in doing so, try to rewrite this in a more usable form. Underneath the square root symbol, instead of writing negative x minus 40, as we saw with transformations when we did them in a previous topic, we're actually going to factor out a negative sign so that we have a positive variable there, or at least it looks that way underneath the parentheses. That will help us determine what's going on with the horizontal reflections that may occur here. So I'm going to factor a negative out, and then after it, I have to write x and then a plus 40, because I better be able to check this, and if I were to distribute the negative sign into these parentheses, I better get what I had in that original expression underneath the root, which would be a negative x minus 40, and of course, when I factor out that negative sign, that does require this to be an x plus 40 in parentheses, following it, all still underneath this root. And then we have the plus 30 just kind of hanging on the end after the root. So now let's recall what our transformations mean for what we're looking at here. The negative sign that's inside the root yet in front of the parentheses that contain the variable, though that would indicate a horizontal reflection. If you go back and look at our transformation notes, you'll find that to be there. And then what's inside the parentheses after the x, so the x plus 40, the fact that it's a plus 40 means we're going to move left 40 units. That's a translation where you just simply slide to the left. And then at the end, this plus 30 would mean we translate up 30 units. So you could say sliding up. And then furthermore, if you consider or recall the parent function, we dealt with several of them early on in this transformation topic. The parent function of this one would be a y equals the square root of x. And as you may recall, the parent graph of that function hits the origin and then takes off to the right in quadrant 1, just kind of increasing but leveling off as it goes. That would be the graph of the square root of x. And understanding what that graph looks like is essential to knowing how we're going to draw this transformed version of it. And as you'll recall, to transform a function, you actually have to follow a certain order of these transformations. And so again, you can go back and review your notes on transformations to know the order of those. In this case, let's go ahead and draw just a blank coordinate grid, our xy coordinate plane, and understand what the parent function is, as we just drew, but then how these changes will be happening. As you'll recall with the order that matters, you have to start with any left or right translation. So I'll put a number 1 by we have to start with shifting left or right. Secondly, we consider something perhaps way out in front of our parent function, but there's actually nothing there. So there's really nothing to do for step 2, which means the third step we do would be right inside this negative sign. We actually do have that to do. So let's actually number these only according to what we have. We'll do the left 40 first. Secondly, any vertical flipping or stretching, that's not happening here. Thirdly, any horizontal, but for us, that's the only thing we have next, so I'll put that as step 2. And then lastly, we're going to have to translate up or down, so step 3 would be adding the 30. If we do those steps to this graph, we'll go left 40. So imagine that. That would take the graph that starts out in quadrant 1 and shift it left 40 units. That'd be at a negative 40 now. And that'd be looking the same, but shifted left 40. So let's keep that in mind. That's all that we have going on so far, but of course there's more to it. So after going left 40, we have to do a horizontal reflection. Well, that means if it's going to the right, it's now going to be going to the left. So we'll also then not only shift left 40, but then also change the directions. So it'd be shooting off to the left instead of to the right. But then lastly, if we're going up 30, then we'd just take that exact shape, shift it up 30. So we'll mark that on our y-axis. And then the graph would look like it has to this point, but now starting at that point of negative 40, 30. And lastly, let's discuss some general nth root rules. And that are these. If n is even, then the nth root of x to the n, okay, so the index of the root and the power of the variable inside match, and they're even, then the result is the absolute value of x. Well, we actually saw that earlier on when we experimented with our definition of absolute value, you may recall. And then secondly, if n is odd, then also in the same case when the index and the power match, but those are both n and they're odd, then the result is just x with no absolute value involved. So whether n is even or odd in these cases makes the difference. For example, if I had the fifth root of x to the fifth, notice those are both odd. That's the case where I do not need the absolute value, so we would just say that's just x. Or secondly, if I had the sixth root of y to the sixth, notice the root and the index match, and they're both even, so that would be the absolute value of y. We would have to put the absolute value with that expression. And then thirdly, if I had the cube root of negative 125x cubed, I could apply the root to each of those factors separately. The cube root of negative 125 would be negative 5. That's because negative 5 times negative 5 times negative 5 is negative 125. And the cube root of x cubed would be just an x without the absolute value given the rule above. And so negative 5x would be our result there. Fourthly, if I had the sixth root of negative 6 in parentheses to the power of 6, all of that is tucked underneath this sixth root. Well, notice the index and the power match, and they're both even. So this is the case above where we'd need the absolute value of this inner expression of negative 6. Well, the absolute value of negative 6 is just 6, so that'd be our result. And lastly, if I had the square root of x squared plus 14x plus 49, so that's a trinomial all underneath the root. You'll recall we cannot split up multiple terms and apply a root, like a square root in this case, to each term individually. It's an all or nothing deal. However, this one is factorable. So x squared plus 14x plus 49, you may recall as an x plus 7 squared. That's a perfect square. If you go back to some factoring methods. And here we are with a square root of something squared where the index, though unwritten as 2, matches the power, which is squared here. Therefore, the result needs to be the absolute value of x plus 7 for this simplified result.